In this video, we'll define the hyperbolic functions hyperbolic sine, hyperbolic cosine, and hyperbolic tangent. We'll define hyperbolic cosine first. We write hyperbolic cosine like this. We pronounce it cosh x, and it's defined using the exponential functions like this. Cosh x equals e to the x plus e to the minus x, all divided by 2. Hyperbolic sine is written like this. There are two ways of pronouncing hyperbolic sine. In this video, I'll call it shine, but you will come across some people who call it cinch. And shine x is defined with the exponential function again, like this. We have e to the x minus, this time, e to the minus x, all divided by 2. Now we can use our knowledge of the graphs of e to the x to work out the graphs of shine x and cosh x. Here I've got some graphs of e to the x over 2 and e to the minus x over 2. First, we'll work out what cosh of 0 is. I'll quickly remind you that cosh of x is e to the x plus e to the minus x over 2. So cosh of 0 is e to the 0, which is 1, plus e to the 0 again, which is 1, all divided by 2, which is 2 over 2, which is 1. So we can mark cosh 0 onto our graph here. Now we can work out what happens as x gets big. We can split up how we write cosh x into this form. We have e to the x over 2 plus e to the minus x over 2. Now we already have the graphs of e to the x over 2 and e to the minus x over 2 here. And we can see that as x gets big, e to the x over 2 gets very, very big. But e to the minus x over 2 gets very, very small. So as x gets bigger, this second part of the sum gets very, very close to 0. So the whole thing gets very, very close to just e to the x over 2. So now we can draw that side of the graph. I'll just turn around the graph so I can actually draw it. Now remember that because e to the minus x over 2 is always bigger than 0, even though it gets very, very small, cosh x will always stay above the graph of e to the x over 2. The graphs get closer together as x gets big, but cosh x must always stay above e to the x over 2. Now we'll see what happens when x gets large and negative. Now, when x gets large and negative, we can see that e to the x over 2 gets very, very small, but e to the minus x over 2 gets very, very big. So writing cosh x again as e to the x over 2 plus e to the minus x over 2, we can see that the first part of the sum this time gets very, very small, and the second part of the sum gets very, very big. So the whole thing as x gets larger and negative, will get closer and closer to e to the minus x over 2. So we can draw in that side of the graph now. Now remember again that e to the x over 2, even though it's getting very, very small, will always be bigger than 0. So the graph will always stay above e to the minus x over 2. As x gets more negative, the graphs get closer together, but the graph will always stay above e to the minus x over 2. So here is a graph of cosh x. Now you can see that this graph is symmetric about the y-axis, and that tells us that cosh x is always equal to cosh of minus x. Now let's deal with the graph for sin x. This time to help me, I've got a graph of e to the x over 2 and minus e to the minus x over 2. Let's see what happens when x equals 0. I'll just remind you that sin x is e to the x minus e to the minus x over 2. So sin of 0 is e to the 0, which is 1, minus e to the 0, which is 1, all over 2. So that's 0 over 2, which is 0. Right, so we can plot that point onto our graph at 0, 0. Now we'll see what happens as x gets large. Like before, we can split up the way we write sin x. So we write sin x as e to the x over 2 minus e to the minus x over 2. Now using the same logic as we did before, and remembering what the graphs of e to the x and e to the minus x over 2 look like, we can see that the first part of the sum here gets very, very big as x gets large, but the second part of the sum gets very, very small as x gets large. So again, for large x, the whole of sin x becomes closer and closer to e to the x over 2. So now we can draw in that half of the graph. Now notice this time the graph will stay below e to the x over 2. And that's because we're taking away e to the minus x over 2. Now let's see what happens when x gets large and negative. Again, just so you can see what's happening, I'll write up our split up form of sin x. Now remember, as x got large and negative, e to the x got very, very small. So the first part of the sum gets very, very small. E to the minus x over 2 got very, very big. So this whole thing, as x gets large and negative, gets closer and closer to just the second bit of the sum, because the first bit is getting closer to 0. So for large negative, x shine x gets very, very close to minus e to the minus x over 2. So we can draw the second bit of our graph in now. Now again, the graph must stay above minus e to the minus x over 2, because e to the x over 2 is never 0, even though it gets very, very small. So that adds a bit on to minus e to the minus x over 2 and keeps the graph above it. Now you've noticed that shine x for large x is close to e to the x over 2. And cosh x also, remember, was close to e to the x over 2 for large x. So that must mean for large x, cosh of x and shine x are very close together. And we can see that if I show you a graph of shine x and cosh x plotted together. Got a slightly different scale this time, so it looks a bit wider. But there's cosh x, and there's shine x, which gets very, very close to cosh x as x gets large. Now we'll define hyperbolic tangent. We can define hyperbolic tangent in terms of shine and cosh. We write hyperbolic tangent like this. And again, there are two possible pronunciations for this. Some people call it tanch, but I in this video will call it than. And we define it to be shine x over cosh x. And again, there's an exponential function definition, which we can work out by looking at this definition. Because this is shine x, which is e to the x minus e to the minus x over 2, divided by cosh x, which is e to the x plus e to the minus x over 2. And that, when you work it out, is e to the x minus e to the minus x, all divided by e to the x plus e to the minus x. Now this thing doesn't look very useful for working out the graph. It's a bit complicated. So this time we'll use the graphs of shine and cosh to work out the graphs of than. Now here I've got a set of axes which I'll use to draw than onto. I've got an asymptote here at y equals 1 and one at y equals minus 1, and you'll see why in a minute. Now remember that for x large, we saw that cosh x was very, very close to shine x. So that must mean that shine x over cosh x must be very close to 1. So as x gets large, we should expect than x to get very close to 1. Now for large negative x, we saw that cosh x was very close to e to minus x over 2, and sin x was very close to minus e to the minus x over 2. So we can see here that sin x is very, very close to minus cos x. So that must mean that sin x over cos x is very, very close to minus 1. So as x gets large and negative, we should expect the graph to get very, very close to minus 1. And now, just to finish off, we'll see what happens when x equals 0. So for x equals 0, x, which is sin over cos x, will be, well, sin of x was 0, so that would be 0. Cos of x was 1. So tan of x when x equals 0 is just 0. Now, putting these three bits of information together, we can plot 0, 0 on there. And as x got large, tan x got close to 1. So we can see this thing getting closer to 1. And as x got large and negative, tan x got close to minus 1. So we can draw this going down towards minus 1. But remember that these never actually reach 1 or minus 1. They just get very, very close to them as x gets large or as x gets more negative. Also notice that tan of x is equal to minus tan of minus x. Now, hyperbolic functions have some identities which are very similar to trig identities but not quite the same. In this video, I'll show you and prove for you 2, and then I'll show you some more at the end, which you can try yourself. The first one we'll prove is this one. It's cos x squared minus sin x squared equals 1. Now, to prove this, we'll substitute in the exponential definitions for cos and sin. So we have that cos x was e to the x plus e to the minus x over 2. And we want that all squared. And we take away sin x squared, which was e to the x minus e to the minus x over 2, all squared. Now notice that in both bits of this, we have the same denominator squared. So we can take that out as a factor. So we have that as a quarter of the numerator squared. So we have e to the x plus e to the minus x squared minus e to the x minus e to the minus x squared. Now we want to expand out these squared brackets. So that is going to be, well, these brackets are going to be e to the x times e to the x, which is e to the 2x. And because e to the x times e to the minus x is 1, and we get that happening twice, we get a plus 2 here. And e to the minus x times e to the minus x is e to the minus 2x. And then we take away this bracket squared, which, working as before, we can see is e to the 2x again. And this time we get a minus 2 here, and we get plus e to the minus 2x. Now we can remove these inner brackets, and we get a quarter of, we'll just take out the first brackets first, e to the 2x plus 2 plus e to the minus 2x. I've got a minus here, so that's minus e to the 2x plus 2 minus e to the minus 2x. Now we've got a lot of things that are going to cancel here. We have e to the 2x minus e to the 2x, so these go. We have plus e to the minus 2x here, and minus it again there, so they go. And then we just have 2 plus 2. So the whole thing turns out to be a quarter of 2 plus 2, which is 4, which is 1. So there we have the proof that cosh squared x minus sine squared x, which is all that, is equal to 1. And one more identity I'll prove for you now is this one. It's sine 2x is equal to 2 sine x cosh x. Now with this one, I think it's easier to start with the right-hand side. So we'll do that again. We'll substitute in the exponential definitions to the right-hand side. So 2 sine x cosh x is equal to 2 lots of e to the x minus e to the minus x over 2 times cosh x, which was e to the x, plus e to the minus x over 2. Now you can see the 2 cancels with one of these denominators. So we'll cancel those and take out this half as a factor. So now we have a half e to the x minus e to the minus x times e to the x plus e to the minus x. And if we just multiply out the brackets, we get a half, get e to the x times e to the x, which is e to the 2x, e to the x times plus e to the minus x, which is plus 1, minus e to the minus x times e to the x, which is minus 1, and finally minus e to the minus 2x. So obviously these ones cancel, and we get this bracket here, which was e to the 2x minus e to the minus 2x, all divided by 2. And that is the definition of sine 2x. So that's the second identity proved. Now here are some more identities which you can prove yourself. The first one is cosh 2x is equal to cosh x squared plus sine x squared. We also have sine of x plus y equals sine x cosh y plus sine y cosh x. And also for cosh x plus y, we have cosh x cosh y plus sine x sine y. And two more. Cosh x over 2 all squared is 1 plus cosh x all divided by 2. And to finish off, sine x over 2 all squared is cosh x minus 1 all divided by 2. Now you can see how similar these are to trig identities. And in fact, the hyperbolic functions and trig identities are very closely related. And you can learn more about that if you go and study complex numbers. And before we finish, we'll look at some other functions which are related to hyperbolic functions. Firstly, some notation. You've already seen me use notation like sine x squared, which means the whole of sine x squared. Just remember that if you see something like sine x with a minus 1 there, that is not equal to 1 over sine x. This refers to the inverse function of sine. If you remember that if we have a function f minus 1, the inverse function works like this. You have f minus 1, the inverse function of x, gives you this thing y, where f of y was equal to x. And the same way, sine with a minus 1 there of x gives you y. Where sine of y was equal to x. We can also define inverse functions for cosh and tan, but for these we have to restrict the domains of the function. For inverse cosh, the minus 1 of x, we need to have x greater than or equal to 1. And for the inverse of tan of x, we need x to be greater than minus 1 and less than 1. Now, some other functions you might come across are the reciprocal functions. Now, these are sech x, which is defined to be 1 over cosh of x. And there are two more of these. There's cosech of x, which is 1 over sine of x. And finally, there's coth x, which is 1 over tan